Hi everyone! Today we'll take a deep dive into the graphs of exponential and logarithmic functions. Let's get started. At the start of your lesson, you had the pre-video activity, the parent exponential and logarithmic functions in base 2. If you haven't had a chance to work on it yet, pause the video to do that now. Now, let's check your work. Evaluating 2 to the x at the positive values 1, 2, and 3 gives 2, 4, and 8 respectively. At x equals 0, we'd have 2 to the 0, which we know is equal to 1. And evaluating at the negative values, we would simply get the reciprocals of the outputs we got for their positive counterparts. Plotting these points gives us this exponential growth curve we are very familiar with by now. Furthermore, as we saw earlier in this unit, we know that as x goes to negative infinity, this graph approaches the horizontal asymptote y equals 0. Now let's look at a slightly less familiar function, the logarithmic function log base 2 of x. Let's start with the easier, larger values. At x equals 8, our output would be log base 2 of 8, which is asking us 2 to the power of what exponent is 8? That would be 3. Similarly, the exponents that turn 2 into 1, 2, and 4 would be 0, 1, and 2, respectively. Lastly, for the inputs 1/8, 1/4, and 1/2, since these are the reciprocals of 8, 4, and 2, the outputs would simply be the negative versions of these same exponents. But wait a second. All these values are looking extremely familiar. Aren't all these the same numbers from the exponential function we just graphed? These are all the exact same points for function a. Well, almost. It seems like the coordinates are switched. All the inputs from the exponential function a are the outputs of the logarithmic function b, and all the outputs of a are the inputs of b. What will this mean graphically? Let's bring back the graph of a. If we grab all the points from this exponential curve and switch their x and y coordinates, we get the graph of the logarithmic function. All this switching is starting to ring a bell. Earlier in this course, we learned about relationships that behave like this. Do you remember what we call them? We call them inverse functions. You might remember inverse functions from Unit 1. We learned that the graphs of inverse functions are reflections of each other over the line y equals x, which is exactly what's happening here. Furthermore, since the exponential function had a horizontal asymptote at y equals 0, shouldn't the logarithmic function have an asymptote somewhere as well? Yes, function b must have a vertical asymptote at x equals 0. This makes sense because switching the x's and y's makes all the horizontal aspects of the function become vertical, and vice versa. Even though here we looked specifically at the exponential and logarithmic functions in base 2, this inverse relationship is true for any base b. In general, we say that the exponential function y equals b to the x and the logarithmic function y equals log base b to the x are inverse functions of each other. Let's start looking more closely at the graph of each function. Let's start with exponential functions. Remember, we have two types of exponential behavior, growth and decay. The graph we have here is an example of exponential growth, which, as we learned earlier in this unit, happens when the base is greater than 1. We saw that exponential functions grow to infinity as x goes to infinity, but they decrease towards 0 as x goes to negative infinity, which is why they have a horizontal asymptote at y equals 0. Since the function never actually reaches 0, there are no x-intercepts, and its range is from 0 to positive infinity, not including 0. What about the y-intercept? By definition, a y-intercept is the point where x is 0, and we know that any base b to the power of 0 will be 1. Therefore, all exponential functions of the form b to the x will have a y-intercept at 0, 1. Lastly, since exponential functions accept all real numbers as inputs, their graphs extend infinitely to the right and to the left, which makes their domain the interval from negative infinity to positive infinity. What about exponential decay? Remember, an exponential function decays when its base is between 0 and 1. All the features stay the same except the end behavior, because exponential decay graphs decrease towards 0 as x goes to infinity and shoot toward positive infinity as x goes to negative infinity. Now let's look at logarithmic functions. However, since we already know exponential and logarithmic functions are inverses, why don't we just predict the features of log base b to the x directly from the features of b to the x we just found? Pause the video and try it out yourself. When we studied inverse functions back in Unit 1, we learned that the domain of a function is the range of its inverse, and the range is the domain of the inverse. Furthermore, since x's are switched with y's, it makes sense that the x-intercept becomes the y-intercept and vice versa. And, as we had already mentioned earlier, the horizontal asymptote at the x-axis, or y equals 0, becomes a vertical asymptote at the y-axis, or x equals 0. As for end behavior, once again we have two types: logarithmic growth, which happens when the base is greater than 1, and logarithmic decay, which happens when the base is between 0 and 1. Inverting the end behavior statements, we get that a logarithmic growth function goes to positive infinity as x goes to positive infinity, which matches what we observed earlier in our graph. As for the other statement, even though it is true that the function goes toward negative infinity as x approaches 0 because of the vertical asymptote, the term end behavior refers only to what happens when x goes to either positive or negative infinity, so we can omit this statement. For logarithmic decay, our graph will go to negative infinity as x goes to positive infinity, and just as with the growth function, we have a statement that describes the graph shooting up toward the vertical asymptote as x approaches 0, which we can omit from the end behavior. Notice how, since logarithmic functions do not extend infinitely to the left, they will only have one end behavior statement, as opposed to two. Now that we know how the graphs of exponential and logarithmic functions look, let's start graphing some transformations of these functions. Let's review quickly how functions are transformed. For any parent function y equals f of x, a transformation of f can be written in the form y equals a times f of b times x minus c plus d. Remember that the operations affecting the output, or outside, will cause vertical transformations, while those affecting the input, or inside, will cause horizontal transformations. A multiplication outside by a number a will produce vertical scaling by a factor of the absolute value of a, and if a is negative, a reflection over the x-axis. A multiplication inside by some number b will produce horizontal scaling by a factor of the reciprocal of the absolute value of b, and if b is negative, a reflection over the y-axis. Adding or subtracting inside the parent function will horizontally translate by c units, while adding or subtracting outside the function will vertically translate by d units. Using this format, it's important to remember that scaling and reflections should always be performed first, and translations performed last. The order in which we perform the scaling and reflections doesn't matter as long as they are done before translations. Let's look at some examples of graphing transformations of exponential and logarithmic functions. Let's look at the function c of x equals 2 times 3 to the minus x minus 4. Our graphs in this lesson don't need to be very exact. We will only focus on drawing sketches that show the shape, the intercepts, and the asymptote of the function. Let's start by identifying the parent function. This is an exponential function with base 3, so the parent function is 3 to the x. It will have an asymptote at y equals 0, and since it's an exponential growth function, we know it will shoot up as it goes right. Now, pause the video and identify the transformations of function c. Function c has a vertical stretch by a factor of 2, a reflection over the y-axis, and a translation 4 units down. The vertical stretch will pull up the graph and make it twice as tall by multiplying the outputs by 2. However, since we're just sketching, we don't need to worry about being exact with this transformation. The reflection, on the other hand, completely changes the end behavior of this function. It turns our parent growth function into a decay function. Notice that the vertical scaling and reflection do not affect the asymptote. But what about the translation? Since we're moving the entire graph 4 units down, the horizontal asymptote will indeed move down to y equals -4. This means the range is from -4, non-inclusive, to positive infinity. Also, we already know that all exponential functions extend infinitely left and right, so our domain is all real numbers. With the sketch we have so far, we can also see the end behavior. As x goes to infinity, c of x goes to -4, and as x goes to negative infinity, c of x goes to infinity. All that's left now is to find the intercepts. From our sketch, we can see there will be one x-intercept and one y-intercept. How can we find these exact points? An x-intercept is when the value of y is 0, so we can replace c of x with 0 and solve for x. Adding 4 and dividing by 2 on both sides, we get 2 equals 3 to the minus x, which leads to x equals negative log base 3 of 2. Putting this in the calculator, we get that our x-intercept is approximately 0.631. To find our y-intercept, we now replace x with 0 in c of x, which gives us an output of -2. Our y-intercept is therefore 0, -2. Our sketch of the graph of c is now complete. To wrap up this lesson, let's graph the logarithmic function d of x equals minus log base 6 of 2 times x plus 3. Pause the video and try it out yourself. Our parent function would be y equals log base 6 of x. Since the base is greater than 1, we have a logarithmic growth curve. And remember, we'll have a vertical asymptote at x equals 0. Now let's identify the transformations. The minus sign outside the parent function will reflect over the x-axis. This reflection will change the growth behavior of our function into decay. The other two transformations we have, the 2 and the 3, since they are inside, they will transform the graph horizontally. Remember that horizontal transformations do the exact opposite of what you'd expect. The 2 that is multiplying inside will horizontally compress by a factor of 1/2, which means it will divide all the x coordinates by 2. And the 3 adding to the input, although we would usually think of adding as moving to the right, it will actually translate the function 3 units to the left, shifting the vertical asymptote along with it. Notice how the only transformations that move asymptotes are translations. The horizontal asymptotes are shifted only by vertical translations, while the vertical asymptotes are shifted only by horizontal translations. Therefore, our vertical asymptote is x equals -3. As we can see from our sketch, the domain of our function extends from -3, non-inclusive, to positive infinity. Since all logarithmic graphs extend infinitely up and down, the range is from -infinity to positive infinity. As for end behavior, we would only need one statement describing that as x goes to positive infinity, the function goes to -infinity. All that's left is to find the intercepts. To find the x-intercept, we set d of x equal to 0. Then we can divide both sides by -1 and distribute the argument. Then rewrite the equation in exponential form. 6 to the power of 0 is 1. And lastly, we isolate x and get that x equals -2.5. Our x-intercept is therefore -2.5, 0. To find our y-intercept, we replace x with 0, which gives us -log base 6 of 6, which equals -1. Therefore, our y-intercept is 0, -1. And there's our complete sketch for the graph of D. In this lesson, we learned that the exponential function y equals b to the x and the logarithmic function y equals log base b to the x are inverse functions of each other. This relationship is the reason why these functions are reflections of each other over the line y equals x. We also learned how to graph exponential and logarithmic functions using transformations and how to find their features. Once you've finished your guided notes, complete the additional practice. After that, make sure to complete the online practice. See you next time!